Cool. So yeah, we'll be discussing the Mind video paper today, and this paper is done by Zijiao Chen, Xiaoxin Xing, and Helen Zhao. And in particular, we are fortunate to have Zijiao here with us, the first author, and she'll be able to help us clarify any misunderstandings with the paper, answer questions. Always a treat to have the actual author with you when you're discussing a paper. So that's really nice. If you want to just say hi, Zijiao.
Hi, thank you for inviting me, Paul. Yeah, it's my honor to be here. Thank you. It's actually my first time to see people interpret like this paper as well. Yeah, very interesting.
Yeah, very happy to have you here with us. Just a little background is that Zijiao is a grad student in Helen Zhao's lab at National University of Singapore. She also released the MindViz paper late last year, which was reconstructing images from brain activity. And then this is an extension which reconstructs video from brain activity. And we're also in the middle of sort of collaboration, which extends the sparse-coded masked brain modeling approach that she first put out in the MindViz paper into a more full-fledged foundation model training. This is one of the projects in the MedARC group. So just to clarify some stuff about the format of this first, is that I will be kind of walking us through this paper, more or less from top to bottom. And this is a journal club. I don't have slides. This is meant to encourage more participation. So I heavily encourage the audience, if you have any questions or clarifications, be more than free to interrupt, and interrupted via audio, preferably, because I won't be looking at the Zoom chat. You can also type in the Zoom chat and maybe somebody else can vocalize what's going on in the chat. And then Zijiao can maybe answer the clarification questions. I will also have some questions, especially when we get to the more method-y parts, which I might make some mistakes in talking about. So definitely also, Zijiao, feel free to interrupt me to correct any mistakes that I make in talking about the paper. Okay, so yeah, to get started, the high-level takeaway of this paper is it's attaining state-of-the-art reconstructions of video clips from fMRI activity. So this is fMRI activity corresponding to the viewing of these video clips inside of an MRI machine. To give a little bit of a history or time course of the progress of reconstructing video from fMRI, the first study to do this, to my knowledge, is the famous Nishimoto et al. 2011 paper from the Gallant lab, where this is what they were able to do back in 2011, which at the time was really incredible that they were able to attain this. Realize that this is not using neural networks. This is not really using pre-trained models at all. It's more of a ground-up Gabor filtering based approach. So, and like averaging classifications from the clips. So really cool that they were able to attain that at the time. And of course, it's been expanded upon subsequently. So then in 2018, these authors used deep learning to try to reconstruct brain activity from video clips. And also it was this group that released the data set that gets used in a lot of these papers, including the Mind video paper. So unlike MindViz unlike the other like image reconstruction papers, which have been using a pretty recent data set, the natural scenes data set, these video reconstructions are all using a data set from 2018. So relatively lower numbers of samples and data quality. So in this paper from Wen et al., you can see that their reconstructions are, very focused on low-level outputs. So I'll quickly find, you can see that these outputs are more so trying to get like object location and also doing semantic classification. And subsequently, other groups have tried to do GAN-based approaches which gets a little bit better. You can see, so the top row being the original video clip. And then most recently, aside from Mind Video, these authors use self-supervision to reconstruct these kind of outputs. And then finally getting to today, we get these kind of outputs from Mind Video. So I think the most obvious difference here is the very high semantic quality of these outputs compared to the previous papers. But even in terms of low-level details, the Mind Video is attaining state-of-the-art across both the lower-level pixel kind of reconstruction as well as the high-level semantics. So the core contributions of this paper are that they have a two-module approach. So first, there is an fMRI encoder, and then there is an augmented stable diffusion model. Those are the two modules. The fMRI encoder consists of a few different parts. One is a masked brain modeling approach, another is using contrastive learning, which we'll talk about. And the stable diffusion model, this is augmented to handle sort of temporal cohesiveness, like having the ability to output videos instead of just static independent images. And like I said, it attains state-of-the-art in low-level and high-level outputs. And finally, there's an attention analysis at the end, suggesting that the model is biologically plausible in the sense of, relating that to the importance of visual cortex and higher-level networks to the quality of the outputs. So this is the main sort of schematic figure of the paper, and there's kind of a lot to take in here. So we'll maybe start with the blue box, I think. So this is the fMRI encoder. So for the fMRI encoder, the first part of this is pre-training with a different data set and going from voxels to token embeddings. And the way that they do this is similar to how they approached it in the original MindViz paper. So I think I'll pull that up here to show how that works. So this is masked brain modeling, which is inspired by masked autoencoders from this paper, where the idea is that you have an input image, the image gets patched and flattened and converted into this latent space through a vision transformer. And so these tokens, some of which are masked, represented by these gray boxes, corresponding to masked portions of the image. The idea is that you can take these tokens and try to feed that through a decoder, which is also a vision transformer, and recover the masked tokens from this latent space, thereby allowing you to recover the original image. So the same approach can be applied from images to fMRI voxels. Voxels, by the way, these are three-dimensional cubic like tissue where we're recording brain activity from the MRI machine. So this is a little bit tricky to really work my head around. So I'm gonna try my best here. So my understanding is that the input fMRI, you're only taking, first off, around 10% of the total voxels of the whole brain. And that's done through some sort of like noise estimation of what voxels are most receptive to the video inputs. Is that correct?
Actually, so for the part A here, we're using the like the visual cortex only, and what we use is a predefined pixelation here. So the predefined pixelation is the 2016 one. So we extract the one with like 360 ROI, and we extract it from V1 to V4, resulting to like around 4,000 voxels here. Yeah.
Okay,
Yes.
so you're only using voxels from V1 to V4.
Yeah. So in this case, only V1 to V4.
Is that also the case for the HCP pre-training?
Oh yeah, this is the part with HCP pre-training.
Okay, so for everything, yeah, okay.
Oh yeah. But for the
Okay,
later part, sorry, for the later part that we use the pair data sets to do the fine tuning, we're actually using it actually depends on what data the data set give us. So usually people will give what they will give us is the activated voxels that use like a statistical map or GLM to extract. Yeah.
oh, so for that, you're using this, that's not just V1 through V4 from parcellation. That's from
Yeah.
like the Wen et al. Authors.
Yes. Yes.
Okay, so that's like visual cortex, I'm assuming, as well as like high level voxels, but not the whole brain.
Yeah, sure. Yeah. Usually that's like depends on the data set. So for like the GOD, it's also like around 4,000-ish. And for both 5,000, what I use is their extracted GLM voxels. That's around 1,000 to 2,000. And for the my video data paper that we use, it's around 6,000 voxels. It depends on data sets. Yeah.
Okay, cool. So you take that
One question.
subset.
What's V1 to V4 like? What do you mean by that?
Oh, that's the region of interest. The name of the region of interest. They are low level visual cortex.
Okay, so you didn't use the whole like each and every voxel. Uh you just use some regions of interest to
Yeah.
mask those voxels. Okay.
Yeah. Because the whole brain, in this population is around like 32,000. If we fit into this architecture, there will be like way more token than we can handle in like our GPU. And also like usually the voxels in visual cortex are more informative than other areas. That's why we use a predefined population to select the voxels. Yeah.
Okay, okay, so the size of the voxels that I use, they're also like 3 by 35,724, something like that.
So it depends on the scanner. So the voxels that are defined here is actually 2 millimeters for HCP dataset.
Oh, okay. So it's
Okay.
different from the national scenes data set, right?
Yes. I believe so.
Oh,
NSD dataset is a 3 Tesla dataset, so it's way higher resolution than the ones that we use here.
okay. Thank you.
Yeah, I
Do you
think
know
it's
how
1.8 millimeter for a natural scenes data set, but the like signal to noise is a lot higher because it's 7 Tesla.
Yeah.
do you know how you find V1 to V4?
So this one is defined by a predefined population. It's called
Yo parcellation, right?
not the Yo one, the Glasser one, the Glasser 2016, the one with 360 our eyes. I'll look it up and send a link to the chat box.
I think maybe I can help visualize this. So like this is the brain, right? This is the back of the brain. So this is like visual cortex here at the back. And so like if you take a brain like this, you can like
Yeah.
visualize maybe where V1 through V4 are on this. So like wait, where did my
Oh yeah. I sent the one to the chat box, and I think Alex helped with that as well. I'll have
Oh, awesome, great. That's weird. Usually there's like a toolbox at the top where I can visualize the different areas, but basically like visual areas back of the brain. So V1 is where my cursor is here, going outward.
Yeah.
Yeah, any other questions before I keep going?
Right. Yeah, I guess that makes sense in terms of where V1 to V4 are. I'm just curious how they find those areas for like each person, but I guess that info's in the paper, so I'll check that out.
Yeah.
Okay, so yeah, so the original population is usually down like in a large group of subjects. They are like project like everyone's brain, say 1,000 or like 10,000 subjects brain into a like standard space, and they do some like functional they define the areas by some functional localizer or whatever, or like some clustering algorithm to like cluster this brain voxels into different small regions. Usually that's how they define this puzzles. Yeah. And the later people just need to like transform the brain into the same space and apply this mask. Yeah. That's what we do here. Yeah, they're kind of like a tool for us. Yes.
Gotcha, thanks.
Okay, thank you.
Yeah. So yeah, and also there's like random topic mapping to like get really better quality delineations between V1, V2, V3, V4. But like for not having to collect additional data where you're doing that, you use like this parcellation approach that Zijiao is talking about. So basically, you're taking a subset of the voxels, right? And my understanding is that you're then flattening them and then patching them. Yes?
Yes. So say for example, this is a 1D vector, and I divided by n times 16. So the patch size is 16, so I divided by n times 16, and I random mass like 90% of the 75% of the n, and I fit into this VIT encoder.
Mm-hmm.
Yeah. Yes.
Okay, so each of these is a patch, and then you do like 1D convolution where patch size is equal to stride to get tokens. And so
Yes, yeah.
that's the input to here. But then some of these are masked, like what did you say, 90% or 75%?
75%. So we only put the non-mass into this. It's like a vision transformer that we have these tokens and we put it into this VIT encoder.
Okay,
Yes. Thank you.
great. So then you get a
I have one question. Oh, sorry. Can I ask one question?
Yeah,
Yeah.
definitely.
Yeah. So like you're doing this training with multiple subjects, right? So like when you are creating these tokens, I would say like I'm curious, like how wouldn't you have some kind of an alignment problem? Like for different subjects, the distribution of all like the token activations would change quite a lot, I would think. Like how, I don't know how it's not causing a problem here.
Yeah, so actually this has like two steps. So the first step in the pre-training, we're actually we just want to have like as much as training set. So we don't care like whether these are very different from different subjects. So for the pre-training set, it's down like across subject. But in the second step that we actually fine-tune this on we fine-tune this on the pair data. We only use like one subject for one model. Oh yeah, we think that like there are
I see.
definitely a lot of like disalignment in like different subjects. That's why we also try like combine them together, but that doesn't work very well. So that's why yeah, we decide to have like one model for one subject, and that's what other works in this area do as well. Yeah.
I see. Thanks.
Thank you. Yeah.
Yeah, great question.
Have you tried other forms of masking, like masking, for example, if you were to mask in like the frequency domain, like spatial frequency domain?
Yeah, yeah, we did try some like other masking strategy. It's basically like based on ROI, etc. But we didn't try like masking on the frequency domain. We did this kind of masking is because of the paper that Paul just showed us. The 2022. The MAE paper that they found that they try various masking strategy and they found this to be optimal, and that's why we follow this as well. And in the supplementary material of this paper, of the MyVis paper, we do have like the result of some other masking strategy as well. Yeah, and we found this aligned with the Hurst paper that random masking is the best in this case. Yeah. Yeah. Thank you.
Thanks.
Thank you.
Yeah, great questions. Definitely keep interrupting me. So then you have these latents, and there's also a vision transformer decoder that will recover the mask tokens, and then you can then go all the way back to the original voxels, and then you can do L2 loss sum of squared errors to train the model. And so this is basically done by itself first using the Human Connectome project dataset. Then it gets fine-tuned on the actual Wen et al. 2018 dataset. And there's this final projector, which changes the dimensionality of the embeddings to, I think it's this 77 by 768.
Yeah,
and then
yeah.
that can then be fed through the contrastive part. Is that all correct?
Yeah. That's all correct.
Okay, cool. Anyone have questions about this before we go on to the contrastive?
Can I just ask a quick question in terms of, are you using voxel level beta coefficients from a GLM, or how else are you defining the voxel level values?
You mean like HCP or like the fine-tuning stage?
No, just in terms of like what each voxel represents. Are you using something like GLM single to get like an image level coefficient or something like this?
It actually depends on like which data set. For the HCP data set, this one is like after the like minimal preprocessing pipeline, and for GOD it's I think for GOD and Bo 5000 they're all like using GLM, the residue of GLM. Yeah, and for the my video data set, that's using the statistical difference between the resting states. The stimuli and non-stimuli. So it depends on the data set. So the reason they are different is it's that we try to like compare with the previous benchmark. So we try to follow what previous benchmark do. Yeah.
Okay, thanks.
Thank you.
Okay, so that's how you get this fMRI token embedding. But then you also have this clip-based part. So you have the video frames, and every video frame can be converted into a clip image latent through a frozen clip. And then also every video frame can be converted into a caption using blip. And then that also can be fed through the clip-based text encoder.
Yeah.
And so are all of these 77 by 768? And then you do contrastive on this?
Yeah. Yeah, we do contrastive on fMRI and image, and also fMRI to text. Since the image to text is already like pre-trained on like huge data set, so we don't think that we have we need to like fine tune on that. So that's why we fine tune on this contrastive latent space. And the reason why is that we want this our fMRI encoder to be close to the image and text space to make it more expressive in this way. Yeah. Actually I think like out for this this figure itself might be slightly misleading. So for fine-tuning the later video diffusion model, we actually use the fMRI embedding as well instead of the contrastive latent space.
Oh, okay.
Yeah, so dimension itself is still 77 by 768.
Mhm.
Yeah.
How do you have a 77 by 768 for clip image? Because I thought the output was like 1 by 768, or like, how are you getting the 77?
Just concat them together.
Concat. Oh, like duplicating it?
Yeah.
Oh, okay.
Yeah.
Also
see.
for like if the for a lot of the video frames, the text caption would probably will be the same, right?
Oh yeah,
So-
yeah. Oh yeah. Oh, okay. Sorry. Please.
So like yeah, so isn't that like we're like using the same data for a lot of frames?
Yeah, actually here we're say here there's only 6 frames in one training sample, so we randomly sample one to get the image and get the image latent and the text latent. Yeah. And also the reason that we do this is because that in this data set they have this constraint that in one short video clip this there wouldn't be like a very sharp scene transition. Yeah, so if this is people doing Tai Chi, then this in this short clip, say in 5 seconds, this people is always doing this this motion. Yeah.
So the contrastive learning is on video frames from different videos, and you're trying to distinguish which are from the same video and which are from different videos, or?
Yeah, exactly. Yes. So the positive pairs are they're the same video. The negative is like different.
Sorry, I'm a bit confused about the dimensions of this contrastive latent space. You said this is 77 by 768.
Yeah. So the reason that the fMRI, the size of the fMRI embedding is 77 by 768 is because the input of the stable diffusion is taking 77 by 768.
I see.
That's why we use that latent space. Yeah.
I see. Okay, thank you.
Yeah. Thank you.
So you basically use clip loss to do what you were saying, like you have the positive pairs of the fMRI corresponding to the correctly paired like video frames. So like these would be the positive pairs along the diagonal, for instance, and then you have all the like negative pairs of fMRI corresponding to different video clips. We try to minimize the cosine similarity of the negative pairs, maximize along the positive pair diagonal.
Yes.
And you do that like with both of these at the same time, the text and the image?
Yeah. So the loss itself is adding the clip loss of fMRI and text and also fMRI to image and divided by 2. So this should be in session 3. Yeah.
Mhm.
Yeah.
Okay, great.
Yeah.
So I thought maybe next I'll talk about what exactly is the pair. What are these paired samples and how do you correct for the hemodynamic response function maybe? So
Okay, sure.
the kind of crazy thing about this paper is that you're reconstructing video, which is like 30 frames per second, but we're collecting brain volumes every 2 seconds. So
Yeah.
there's an obvious problem here of you have like less than a 1 frame per second kind of brain acquisition. So how do you predict multiple frames given a single sample of a brain volume? Also, the brain activity is lagged and kind of smoothed just as a byproduct of fMRI giving you like blood oxygenation levels that are byproducts of the lagging kind of hemodynamic response function. So in other words, so let's say that the x-axis of this figure is seconds. So like 0 seconds, 2, 4, 6, 8, 10. every one of these video frames, you're downsampling the frame rate to just 6 frames for each of these like 2 seconds periods. So 3 frames per second.
Yes.
And then you also have a TR, the acquisition of the brain volume every 2 seconds. So you have 1 full brain volume for each of these.
Yes, yes, yes.
And so you can't do this because the brain volume activity is not corresponding to this. It'll be corresponding like 6 seconds after. So you actually have to do like this corresponds to 2 for this corresponds to this essentially.
Yeah, and also the next.
But in addition to that, you're also doing a sliding window, right?
Yeah, yes, yes,
So,
yes.
so for the model, you're inputting not just this pair, which I think you call the fMRI frames pair. And yeah. So in addition to that, you take a sliding window. Is this how it works? Like you take the last, say 2
yeah,
paired
actually, sorry. Actually, this sliding window is that say we kind of know that this lag should be around like 6 seconds around that, but when we do the 6 second with we still see a lot of variations because we realize that each individual and even for the same individual at different time point they have like slightly different hemodynamic response. That's why we feel like okay, maybe we can including like the near frames as well to like 1/6 frame of video. So in this pink box is that say for example up there it's 3 fMRI frame and down there is actually one fMRI frame pair. That's like a 1/6 frame box.
Oh, so like this or the opposite?
Yeah, like this, yes. Yes. Yeah.
Okay. So is this a sliding window of 2 or 3?
Yeah, we try like 0, 1, 2, 3, and we found okay, 2 is the best.
So is this is 2 then, having this
Yeah,
window
4
size?
seconds. Yeah, 2. So from 8 to 10.
Okay. All right, cool. Any questions about what the actual input samples are? Okay, so that's what actually gets used as the inputs here, accounting for the lag and also having the sliding window. So my understanding is that like for every pair, which for every like input, you have batch size by sliding window, by patch, by embedding dimension.
Yeah. Yes.
And so then what you do for the spatial attention and for the temporal attention is you kind of split this up into 2 different matrices. So for this is the spatial matrix, spatial, you merge the N and W together like this. And for this, you merge the N and P. Is this correct?
So N is batch size and W is
The window?
a window. Okay. I think for the spatial, it doesn't have the window. It's the spatial is still the same as the original MyVis one. So it's a 1D thing. It's like just like go through every 4,000 voxels.
Oh, okay. So then what is this X spatial that you talk about?
X spatial is actually just the same as the previous one, the self attention of the fMRI itself.
Oh, okay.
Yeah.
Okay, so then, yeah, so we have all these possible inputs, I guess, and then, sorry, what's the average fMRI here?
So the average fMRI here is that so previously in MyVis we have this time step conditioning to make this the guidance stronger in this downstream generation. But later on, people found this to be like not elegant enough. So later on, they just use like something called adversarial guidance. So this adversarial guidance is usually telling you what to not predict. This is kind of the negative prompt. In NLP, it's kind of like not to do something. So it's basically telling you like this is not correct. And in this situation, we're thinking like what is like meaningful but not correct. We actually at that time we think about like just using 0 or 1 or negative or something. But because that's like not oh sorry my cat because that's meaningless, so it doesn't give like strong enough guidance. So what we think is that okay, maybe we can like get a fake fMRI to say that this is not the correct one. So what we do is that we average the test fMRI to make it a negative prompt. Yeah. So you see in page 5 down there, you see the updated loss is that every time what they do is that every time they have a fMRI and they minus that, that's usually how they say that okay, we're not predicting to that. Yeah. Yes.
Okay, great. So then I guess for the augmented stable diffusion part, this is stable diffusion 1.5 that has been augmented in the sense of like tuna video. So you have the ability to have this sort of temporal coherence by using a pseudo like 3D layer.
Yes.
And you then can fine tune that augmented stable diffusion by fine tuning the like self attention and cross attention and the temporal heads of this new augmented part of the model.
Yes, and one thing that this paper proposes the sparse causal attention that where they greatly reduce where they can like rely on the previous time points, but like greatly reduce the computational cost. The sparse causal attention. That is that in the full attention that it's usually like aligning for all the previous frame. Say they in the full attention that is frame 3 is depending on frame 1 and 2, frame 4 is depending on 1, 2, 3, 4, and what this SC attention do is that they only depend on the previous 2 frames. Yeah, they do.
Yeah, this part.
Yes.
Yeah, so tuna video uses like previous frame and first frame. You don't use the first frame, you use the past 2 frames.
Yes. This is actually by experiments.
Yeah, you tested it out and so that seemed to be working the best.
Yeah, seems to be like more consistent in this case.
Okay, great. So I believe that's basically the gist of the methods of how this has worked. Is there anything you want to like add on to that might be informative for interpreting the pipeline of this?
Not that I can think of. Like, yeah.
Okay. And any questions from the audience before we move on? Okay, so I guess to summarize here, the structure of this is that the fMRI encoder first gets pre-trained on HCP, a larger data set, it's fine-tuned on the specific fMRI video data set, and also using contrastive learning to get into a basically creating a new multimodal space within CLIP, that is brain space, and then tuning everything together with the augmented stable diffusion with this temporal component so that you have the coherence of the outputs. So then let's talk about the results first, I think. So let's look at figure 4. So here are the mind video outputs compared to the previous papers that have done reconstructions of video. And you can see that the semantic outputs are way higher quality, but also the low-level perceptual outputs, they're not great, but compared to the previous methods, still are outperforming, as shown in this figure, where SIM is the sort of perceptual pixel level metric of structural similarity, where even then the previous state of the art from Cooper-Schmidt is being outperformed by the mind video, specifically for low-level outputs. And then this table shows the sort of semantic level accuracies using classification and all these different ablations of the model, trying out different things like removing contrastive, etc., and showing the full model's performance at the top here. So yeah, doing quite well. And then they end the paper with these interpretation results, where you can look at the attention outputs and take the sum of normalized attention within the different parcellations and display things on a flat map and look at how the attention seems to be progressing both through like the development of the model training, as well as where on the brain the activations of the average attention across the samples is. So they talk about 3 different conclusions based on these attention-based analyses. So one is the dominance of the visual cortex. So as you would expect from watching a video, the visual cortex was very important to like the voxels in visual cortex were very important, as shown from the outputs of the attention. So both visual cortex and also I believe the higher cognitive networks like dorsal attention network were being most involved. So this is parsimonious with what you would expect from theory of vision and higher level functioning being important. For the layer dependent hierarchy, they show the different layers of the fMRI encoder and how that corresponds to like where in the brain it seems to be most important. So for the early layers of the network, so panel A and C here, they see a focus on structural information of the input data and clear segmentation of different brain regions by attention values, aligning with the visual processing hierarchy. And as the network dives into the deeper layers, D and E, the information gets more dispersed and the distinction seems to diminish, indicating this shift towards more abstract processing. I guess one question I have is this clear segmentation of different brain regions by attention values. So like, what exactly are you talking about with this clear segmentation? Are you talking about like the demarcation of V1 to V2, or more generally like visual areas compared to non-visual areas?
Oh, we're actually thinking like the lower visual area and the higher visual area. Say in this top here, you can see that in this attention map that the very distinct values means like they has the most important areas, and we can see that we see V1, V2, V3 is very distinguished from like visual peripheral whatever or V4. we
So
can
you're
see
talking
this.
about this dark area compared to like where V4 is here.
Yeah, yes.
And in the other ones, it's not as clear of a difference of like this gradient. I'm guessing
Yeah,
what the contrast of super dark red to yellow
yeah,
versus a
yeah,
bit lighter red.
yeah, and it's like more widespread.
Mhm.
Yeah, that's actually what we're thinking about. Yeah. This is actually we think this this property is actually the property of transformer or CNN. It's actually not really about like this brand related properties. So for example, if you do visual if you do like this attention map on a regular image, you'll also see that as well. The first layer will capture the structural information, and later on this attention map will be like more widespread. Yeah. So this layer dependent hierarchy is actually about the VIT itself.
Yeah, how the VIT is like transforming across like
Yeah,
over the course of the training, as well as like later layers being more abstract.
yeah, exactly.
Kind of matching how like the brain itself has a
Yeah.
hierarchy.
Yes, exactly.
And so in addition to that, you analyze first layer attention. You analyze the first layer attention after all learning stages, or I guess a better way to state that is you separately analyze the attention before contrastive, after contrastive, and the final model outputs. And you see that before you do contrastive learning, it's less abstract. Like the visual cortex, viz, is showing the most attention value for like before contrastive. But after you do the full model training, it seems to be more so caring about like dorsal attention networks and more abstract information of the video.
Yeah. The semantic information.
Yeah. So that's a nice sort of progression that you're able to uncover by, I guess, probing the attention of the model before and after training.
Thank you.
So I think that's about it for the paper. The final conclusions are, showcasing this novel pipeline, the ability to do pre-training and contrastive loss using an augmented diffusion model to have coherent temporal outputs, getting state-of-the-art both in low level and high level for video, being able to work with video in the first place based on how difficult it is to account for the hemodynamic response and everything. Some limitations are, like you said, generalizability across participants. How might you use more of the brain instead of just the small subset of voxels that seem to be pretty useful for this task? And you also talk about some broader impacts of how this could lead to even more promising large model developments in the future, potential work with brain-computer interfaces, etc.
Yeah, that's a format.
So yeah, that's the paper. Thanks for helping us discuss, and I think we'll open it up to more broad questions from the audience if anyone has questions.
Thanks for this. Oh, go ahead.
Sorry. Go ahead.
I was just wondering, did you do any ablation studies with respect to the pre-training?
For the pre-training, actually, this part was done in MyViz, so we didn't discuss this again. Like, if you go to the MyViz paper and you will see, we actually have a very we have a full ablation study in our stage A. Like result.
Cool, thanks.
Yeah, this one, the left one. Yeah. And in the supplementary material, we also have some additional ones as well.
So I was gonna ask, when I see the results, as you said, there are some quite improvements in also the low level layout prediction, and I'm trying to understand like where this information comes from, because like I see like the clip-based text encoder, and I think you said that for the clip-based image encoder, you are repeating the first embedding of that like clip image encoder, which is mostly related to the semantics rather than where the object is. So I don't know, like where does this low level information come from? Is it coming from the training of the, I don't know, I think you are also training the unit of the stable diffusion, right? Like, are there some
Yeah.
Mhm.
Yeah, we do think that our model is like a lot better in semantic semantic match like than the low level improvement. So we actually see that well, I think like maybe because like the previous benchmark like didn't like successfully generate some like images. So even though our model is not so good at like low level reconstruction, we still feel like we still can say that okay, it's still better than the previous benchmarks. Yeah, but we do admit that okay, our model is like a lot better in the semantic reconstruction than low level generation. Yeah, I think this is one thing that we definitely need to work on as well. Say some.
So,
yeah.
I see.
Some
So like
control.
if we, for example, somehow included more information about the low level layout and information, it would be also better at predicting the location of the objects, you mean, right?
Yeah, I think
I
that's
see.
very important as well. Yeah, we're yeah also thinking about doing this as well.
Yeah, that will be great. Yeah, good luck.
Thank you. Yeah.
Yeah, I guess relatedly, with the MindEye paper and with the brain diffuser paper too, the taking of not the final output of clip, but the last hidden layer of clip retains a lot of the more less semantic, more image-based information. So maybe that's an easy way to kind of like, I guess you'd have to convert that from whatever the like 257 by 768 into 77 by 768, and then use that for the contrastive. But that would be like, I guess, a somewhat easy way to like retain more of the perceptual details, maybe.
Yeah, sure. And maybe some other oh, we actually haven't like done this yet, but like we're also thinking like it say in the contrastive pipeline, maybe we can add some laws that constrain this specifically. The location of each object, the color contrast and everything. Yeah.
Any other questions from the audience?
Yeah, so I had a question about the masked autoencoder. So the masked autoencoder was trained on HCP, and it was fine-tuned on GOD dataset, GOD.
Oh yeah, in this case, in this one, in this video data set is fine-tuned on the 2018.
Okay, so I'm not really I don't know the specifics of these data set, but so the fMRI readings of these two data sets, are they of different resolution? So is that something, was that a problem to get it fine-tuned if it's trained on a different resolution, like pre-trained on a different resolution?
Yeah, so for the resolution, like there are different aspects of the resolution. So the first thing is the scanner. So the scanner is roughly at the same resolution, but like the number of voxel that we extracted are actually different, but this is fine because we're actually fitting in patches instead of voxels. So as long as we fit into n times 16, then it's fine.
Oh,
So,
okay.
yeah, the number of patches doesn't need to be the same for each fine-tuning data sets.
Right. Thank you.
Thank you.
Do you think it would help if you maybe were in the same anatomical space and you had patches that did actually correspond across data sets?
Yeah, we think this might help. Yes. So yeah, I think Jonathan is briefly working on this direction as well.
Oh, interesting.
Oh yeah, I saw a question in the chat box that asking like about high density EEG. Is it possible to use a similar approach and reach comparable results from sensors EEG? So what do you feel like, Paul? I actually haven't done much on EEG, but like I saw that paper that used EEG to reconstruct image, and the result looks very well. Like yeah, very impressively well.
Yeah, I'm also impressed by the recent EEG kind of
Yeah.
work, but I'm also kind of less, I'm not as optimistic about the future of using EEG just
Yeah.
because of like various problems with source localization and like the spatial resolution and everything. So, I mean, I think it's incredible that you're able to get basically anything that is really like resembles the original inputs with EEG. Just yeah, because like the quality of the data that you're getting is like for this kind of task, you do kind of need that high resolution spatial information. I feel obviously it can be proven wrong as more papers come out. Maybe an optimal middle ground is kind of like either adapting things so that you can record EEG and fMRI, like MEG might be a good middle ground, fNIRS might be a good middle ground. Yeah.
ECOG and or other modalities together to get a shared latent of one subject. And maybe
Yeah, like multimodal ways of like you could maybe even align stuff. You might not even have to collect it at the same time if you do.
Sure. Of course, yes. Yeah, that'll be very interesting.
Do you have like a back of the envelope? Oh, sorry, go ahead.
I'll just add like ECOG, obviously the best data quality, but way harder to get ECOG, and it's also not whole brain. So there's always like this kind of data quality versus how hard is it to collect problem.
Sure. Yeah.
Do you have like a back of the envelope estimate in terms of what spatial resolution you'd need fundamentally to do this task?
I actually quite curious about like the portable fMRI. I wonder like whether that could work. If that could work, then that would be very amazing. But my personally, I don't have like a very accurate estimation. Yeah. What about you?
I think well with fMRI, right, we have like with 7 Tesla, you can get 1 millimeter to 2 millimeter. You can get like even sub layers of cortex. So I think there's a lot more still to be done even within that realm to see what maybe like the upper limit is, especially if there's even more training data of what the potential is with that method. With fNIRS, you're going from fMRI being around 2 millimeters, fNIRS maybe like 1 centimeter. So it's quite a big difference, but it still might be doable. With EEG, there isn't even really like a number that you can associate with this because of the source localization problems. You can kind of like look at posterior versus, different like temporal or frontal, but you're not really getting like a metric of like 1 centimeter kind of isolated activity. So it's not even at that point, it's more of just like you really can't even isolate to like the specifics of spatial location. So I think it's kind of an open question of maybe you can reduce the coverage of like 2 millimeter to 1 centimeter if you have enough data, or if you're able to use higher quality data to sort of inform the lower quality data. Kind of an open question at that point.
Yeah, sure.
I guess one very rough estimate that I have, or like one way of framing this question, which is very approximate, but like if I want to reconstruct a 1 megapixel image and I subsample the image to be like 10 by 10 pixels or something, maybe that corresponds to like a spatial resolution of like 1 centimeter or something, if like my visual cortex is maybe 10 centimeters or 3 centimeters, whatever the dimensions are. But one way to think about it is in terms of like blurring an image. Like if I blur an image to be 10 pixels, 10 by 10 pixels, like what is that still reconstructible? How exactly that maps to brain activity, I guess, is ambiguous, but.
I think you wouldn't want, it's sort of like you have a high quality image, let's say, and then you have brain activity. In theory, all you would need to like reconstruct just like the pixels would be really high quality coverage of visual cortex. Like specifically the fovea is where like a ton of the brain is being involved with the processing, and then it kind of blurs out naturally into the periphery. And basically what we're finding with these kind of models is that like you have the ability to make the image quality a bit better by using higher level processing like semantics. But then there's other approaches that are really caring about low level features and being a generalizable model. And then just as an artifact of the data quality, you get blurring. So I think it's sort of like, how much blurring are we currently getting with those kind of lower level approaches? And does that translate to maybe like 10 by 10 pixel image? Maybe. What are your thoughts?
Sorry, I'm like a bit disconnected, like in the middle. So yeah.
It like basically we can already reconstruct blurry images, right? So I guess you could find a correspondence then with like what is the amount of Gaussian blur that you can apply on an initial image to like get the respected output. But if you actually showed blurry images to people in the scanner, it would probably output even worse blurry outputs.
Yeah. Sure. Yes. Yeah.
Okay, any other questions? I guess we have hit the hour mark.
Yeah, just a final question. I feel this is already answered, but sorry to have to repeat this. So we have the image and image embedding and the fMRI embedding. So was there any issue with these embeddings being disjointed? So how were they like they were like aligned to each other? Because I feel like in MindEye we used the diffusion prior for that thing. So I was wondering if there was any issues with having disjointed sets of these embeddings.
So for the image embedding, you mean the embedding in the diffusion model side, or like in the clip space alignment side?
Yeah, go ahead.
Oh yeah. So actually here, I think it's a bit different from the MindEye one, if I understand correctly. So what we do here is that we replace the whole text encoder with the fMRI encoder here. So so what the original like stable diffusion do is that they use this fMRI they use a text embedding to condition on the stable diffusion to fine-tune some of the attention heads there. And what we do is that we use this fMRI embedding to like as a condition to fine-tune this attention heads. Yeah.
Okay.
Yeah. Okay.
Thank you so much.
Thank you. Yeah.
So So that I'm understanding right, I think like what's being talked about here is this part of the like outputs of the contrastive latent space and how like in clip space you have disjointed embeddings as the
Oh.
output of contrastive training. Like even clip images and clip text latents are disjointed, and automatically you're
yeah.
going to have disjointed fMRI latents as well if you do the same sort of clip loss. But you're not feeding in those latents the same way that MindEye feeds in those
Yeah,
latents. And so I'm guessing that you don't then have to, like for MindEye, we had to do this diffusion prior, essentially minimize the mean squared error so that they are kind of interchangeable latents. But you're fine-tuning like the entire unit.
Yeah, part of
part of the unit. So I'm guessing like it can learn to be able to handle the new kind of those changes.
Sure. Yeah, and I also think that like diffusing from a prior is a very brilliant idea as well. I think it's very very good to let it to start from like kind of blurry images and use that to guide the later generation. I think that's like yeah, this can be fast and can be like accurate in terms of like low level features. Yeah.
I guess what you mean is like the low level features of Mind Video are better than the others, but it's still not that great. Maybe one way to make the low level metrics better would be to have like what was done in MindEye or Brain Diffuser of like having a specialized low level output to inform the full output.
Yeah. That's what we think. Yes.
Yeah. So I guess there's a couple different approaches for improving this. There's that. There's like having more informative inputs into this space. There's
Sure.
there's a variety of different possible future directions. Are you intending to continue like improving this?
Yeah, maybe like not at this moment though. Yeah.
Well, it's really exciting. So we'll definitely keep interested in the outputs from you and your lab mates. And let's all give Zijiao a great virtual round of applause for coming with us. And thanks everyone. Also really great questions, by the way, from the audience. So I think this was a great discussion. I personally learned a lot more about the paper. So yeah, thanks everybody. And we'll talk again.
Thank you so much.